Well, good evening, everyone. It's great to see you here. I am very, very excited about tonight because I have surrounding me here an illustrious panel of some of the world's best and some of the world's most important, I should say, particle and accelerator physicists who are working on the next generation after the Large Hadron Collider. So just to get a little bit of a status of where we're at, can I see a show of hands for how many of you have heard of the Large Hadron Collider before? Good, the media has done its job. Excellent. Okay, so my name's Suzie Sheehy. Thank you, Martin, for the introduction. I'm an accelerator physicist at the University of Oxford, and I tend to design smaller machines for different applications, which is what a lot of our project called Accelerators for Humanity has been about. But we couldn't be talking about particle accelerators unless we really brought out the big guns and talked about accelerators for particle physics. So I think you're aware already that the Large Hadron Collider is the highest energy hadron, that is proton collider, ever built, 27 kilometers in circumference underneath the border between France and Switzerland near Geneva. And it is doing a fantastic job at colliding protons together and uncovering the secrets of the universe. But I'm often asked when I talk about particle accelerators, well, what's going to come next? What is the next big thing after the LHC? And that is effectively what we're here to talk about. So the four people I have surrounding me, I'll just give you a quick introduction to each of them, and then I'm going to ask them to introduce their kind of pet project or their ideas on what might be coming after the Large Hadron Collider. So furthest on your left, my right, is Professor Phil Burrows. Phil is a professor in physics at the University of Oxford, and he's also the Associate Director of the John Adams Institute for Accelerator Science, which is one of two accelerator institutes in the UK, and it's also the one that I work in. So Phil's actually in my department. So Phil actually did his degree and PhD in particle physics first at Oxford Uni, and then he actually moved to the USA for about a decade, working at MIT and on SLAC, the linear collider, which was the first electron-positron collider in the world. He then returned to Oxford, then became a professor at Queen Mary University, and then came back to Oxford again. You've spent a lot of time in Oxford, Phil. As a professor and in his current position as director of the John Adams. So Phil has been PI, that is principal investigator, of the UK's team on linear electron-positron collider development and working on the International Linear Collider and the Compact Linear Collider, which he'll explain a little bit more about what those two projects are. He's been principal investigator of the CLIC UK collaboration since 2011, and since 2014 has been the spokesperson of the CLIC, that is Compact Linear Accelerator, collaboration, which involves about 300 people, 60 institutes, and 31 countries around the world. Right, so that's Phil. Could you welcome Phil? Give him a round of applause. Thank you. Okay. So the next person along the line is Dr. Frank Zimmerman. Now, I'm particularly excited to have Frank here because Frank's actually come all the way over from CERN. Frank is a senior scientist at CERN in the Accelerator Beams department, which is obviously the home of the Large Hadron Collider. Frank has worked, it seems, on just about every major project going. Did his PhD at the University of Hamburg on a machine called Hera, which is a proton ring, and has worked at major labs around the world, including DAISY in Germany, SLAC in the US, and has worked at CERN from 1999, I believe. So Frank has published textbooks in accelerator physics, wrote the handbook. He's the editor of the main journal in the accelerator field, the Physical Review, Accelerator and Beams. I know you're going to rush out and read it right now. It's good. It's a good read, Frank, isn't it? It's good. He's also coordinator of a work package of one of the major European coordination in accelerator research and development called EU-CARD. The work package is called Extreme Beams, which is kind of cool. I like it. And since 2014, has also been deputy coordinator of the CERN-hosted Future Circular Collider study, which is mostly, I think, what you'll be addressing tonight, hopefully. So please welcome Frank. Okay, so first on my left, your right, this is Professor Ken Long, who is a professor of particle physics at Imperial College in London. And he's done a lot of work at CERN on muon proton scattering as a graduate student, apparently, and and then returned to the UK to join an experiment at DAISY in Hamburg. In fact, these two discovered they were almost colleagues at DAISY by 1 year, I think, we discovered. And has contributed to the design and construction of that experiment, so that's particle physics experiment. Now, Ken got fascinated by the discovery of neutrino oscillations at one point in career, and your career seems to have turned direction and really focused on neutrinos and muons since that time. So Ken chairs the international design study for a machine called the Neutrino Factory, which hopefully we'll hear more about, and is spokesman for an experiment called the Muon ionization cooling experiment, which is being carried out at the Rutherford Appleton Lab in Oxfordshire. And is also chair of the International Committee for Future Accelerators Neutrino Panel. So Ken focuses mostly on neutrino and muon accelerators at the moment. So please welcome Ken. And finally, but by no means least, Stuart Mangles, Dr. Stuart Mangles on my far left here, is a senior lecturer in physics at Imperial College London, where he also did his PhD, and he's a faculty member of the John Adams Institute as well, I should say. Now, Stuart's focus is a little different from the other four of us here, in fact, in that he's actually, by definition, a plasma physicist, I suppose. So he researches plasma-based accelerators, and he's been doing that for the past 15 years, using a technique called laser wake field acceleration. So Stuart has a growing interest in that field, in both developing laser wake field accelerators, both for particle physics and for other applications, and improving the quality of the beams from them. He's also involved in a project at DAISY Lab, DAISY keeps cropping up, doesn't it, called Flash Forward, which will use intense beams of electrons to drive a plasma wave. So that's not going to make a huge amount of sense right now, but it will when Stuart gives us a bit of an introduction later. So please welcome Stuart. Thank you. Okay, so that is my illustrious panel, which is why I'm so excited to dig into some of the science behind what they do. So what I asked each of my panel to do is actually basically provide a 5-minute kind of introduction pitch to the types of projects that they work on and that they think might happen in the future. So the first contribution to that is Phil Burrows. So hopefully we have some slides to go along. Over to you, Phil.
Okay, thank you very much, Suzie. Is the microphone working? Can everybody hear me? Okay, super. Well, ladies and gentlemen, thank you very much for giving up a rather lovely Friday evening in September to come and join us in this conversation about possible future large accelerator projects. Now, you've already identified yourselves as a very erudite audience because everybody's heard of the Large Hadron Collider, and everybody knows that large modern high-energy particle accelerators are circular, such as the LHC that you see on the photograph here. Well, they're circular, that is, except when they're not. And so this is a photograph of the 2-mile-long linear collider at Stanford in California. And in fact, Frank and I had the privilege to work together on this project in the 1990s. And you can see manifestly that it is linear, it is 2 miles long. So, what do we do? What do we want to do with linear electron-positron colliders? Well, we want to take subatomic particles, electrons. We want to collide them with their antimatter partners, positrons, which have the opposite electric charge. When electrons meet positrons, matter and antimatter annihilate, energy is released, and what condenses out of that energy are exciting types of new elementary particles, for example, the Higgs boson, which I'm sure most of you will have heard of, that was discovered only a couple of years ago at CERN. For example, top quarks, which are very heavy types of subatomic building blocks of matter. And of course, who knows, maybe dark matter particles, supersymmetric particles, something that has yet to be discovered, about which we would be very excited and very keen to know. So linear electron-positron colliders are the way forward to serve as factories for mass-producing Higgs bosons, top quarks, and hopefully dark matter and other types of new particles. We're talking about hundreds of thousands of Higgs bosons, hundreds of thousands of top quarks, samples that will allow us to really measure the properties of these particles with exquisite precision and understand what they are. Now, there are two major projects which are being proposed for implementation for high-energy future E+, E- electron positron linear colliders. This one is the International Linear Collider. To cut a long story short, you stick electrons in at one end, you stick positrons in at the other end, you accelerate them together, and you do matter-antimatter annihilations in the middle. The rest of the detail you don't need to worry about. The footprint of this machine is about 30 kilometers. Our friends in Japan have the particle physics community in Japan very much wants to host this machine in the northern part of Japan, just north of the city of Sendai. You can see on the map there the footprint of the machine. If you look closely, you can see a cross-section through the geology of the mountains in the Kitakami region. So this project, we hope very much, will be realized in Japan. Now, another project, which is perhaps a little bit further away, is the Compact Linear Collider. And as Suzie said, I'm privileged to be the spokesman, or if you like, principal investigator of this project. Again, don't worry about the details. It's a slightly bigger version of the International Linear Collider. It's designed to get to somewhat higher energies of these collisions. And never let it be said that accelerator physicists don't have a sense of humor, because compact means 50 kilometers long. But that's a jolly sight more compact than it would be if it weren't made with this wonderful technology. As Suzie mentioned, I think it's important to note that these are global-scale projects. So in the case of the Compact Linear Collider, 300 people, 50 institutes, 31 countries. So my joke at this point is the sun never sets on my empire. Now, if that project were realized, it would be realized in the Geneva region at CERN. So here you see a little map. The little white circle in the middle is the Large Hadron Collider. And then you can see magenta, green, and blue linear arrays of dots. And those represent the different stages of this project, leading eventually up to an energy of 3,000 giga-electron volts, or accelerating particles, to energies of 1.5 trillion volts for the electrons and 1.5 trillion volts for the positrons. So these are very high energy machines. So what I would hope to argue this evening is that the way ahead is linear. Linear colliders allow collisions of point-like particles under controlled conditions. They allow factory-level production of things such as Higgs bosons, which we really need to understand, having just discovered them a few years ago. Why linear? The problem, and Frank, of course, will talk about this in his presentation, when you try to accelerate electrons or positrons in a circle, they emit X-rays. This is called synchrotron radiation. And at some point, as fast as you're trying to accelerate them, they're radiating energy away. And so it's generally agreed that to get to the very highest energies, one should avoid this synchrotron radiation, and therefore the future is linear machines with no synchrotron radiation. They're elegantly expandable because you can always make them that bit longer and therefore get to higher energies. And they are intrinsically upgradable because once you have your nice 30-kilometer long tunnel, when Stuart comes along in 50 years, when his technology is working, you can always stick it in to this beautiful tunnel, and you can get to higher energies by upgrading the facility that you have as technology comes along and as you're able to get to higher and higher energies. So elegantly expandable and intrinsically upgradable. And the technologies that we're developing have many applications. This is my last couple of slides, Suzie, as you know. So this is the European X-ray free electron laser at the DAISY laboratory again in Hamburg. And the technology that we've developed, superconducting niobium radio frequency accelerating cavities, the shiny thing bottom left there. This technology developed for these big high energy machines such as the International Linear Collider has now been deployed in a 2-kilometer machine in Hamburg. It's a 10% scale model of the real ILC machine, and this will serve tens of thousands of scientists by producing X-rays to look at the structure of matter, materials, do structural biology, do biomedicine, chemistry, and so on. So this is an example of the spin-off of the technology for the great benefit of wider science, and I love this slide. This is another example of the application of linear accelerating technology. The gentlemen in the bottom left are carrying a roughly 1 meter long accelerating structure made of copper. They've developed structures like that for the purpose of getting to high energies, the big 2-mile-long machine at Stanford that you see upstairs. And today, there is one of those structures in more than 10,000 X-ray therapy machines that are deployed in hospitals all over the world. There are more than 10,000 of these machines worldwide. And in the UK alone, 10,000 people per day are treated with cancer therapy from machines like this, which are employing technology developed with a view to very high energy linear colliders. So I think at that point, I'd better stop, and I'll give my colleagues a chance to get their 10 cents worth. Thank you.
Wow, right. What a sales pitch. Okay, so having heard the sales pitch for linear colliders, as I said in my introduction, at the moment there's a large study at CERN happening for a circular collider instead. So, Frank, over to you.
Okay, thank you. Of course, I disagree with the statement of Phil that the future is linear. Maybe, can I stand up here? I have some problem with the eyesight. It's difficult for me to see on those screens. Okay, here you see a history of colliders, electron-positron colliders in blue, and center of mass, and Hadron Colliders, proton colliders in red. And this is a logarithmic scale of the center of mass energy. So it's over the last 50 or 60 years, you can see dramatic progress in the collision energy. So we got a factor 1,000 or so in the energy of electron-positron collisions, and a factor 100 in the energy of hadron colliders, slightly above 100. And there were not so many. As you can see, there were not so many hadron colliders, and there used to be more electron-positron colliders. So, and these colliders were extremely successful because they allowed us to construct the so-called standard model of particle physics. In the standard model, we have the matter particles, which consist of quarks and leptons, and we have force carriers, which are these bosons here. And then there is a different particle, the Higgs boson, which is neither matter nor force. It is completely different from the others. So all the heavier particles here were discovered at colliders. The Spear collider at STFC discovered the charm quark and the tau lepton. Petra discovered the gluon. That was in Europe at DESY. That was the only such discovery which didn't give a Nobel Prize for some reason. Then the SPP by S at CERN discovered the Z and W boson. The Tevatron discovered the top quark, and then the LHC, as you may know, a few years ago, it discovered a new particle, the Higgs boson. So the colliders were essential in unraveling this part, the heavier part of the standard model, and they have proven a powerful instrument for discovery and for precision measurement. Okay, but still, we have the standard model, but many questions are not explained by the standard model. Here's an incomplete list. The standard model only describes the known matter, the visible matter, which is about 5% of the universe. There's a large part which is called dark matter, which is visible in the rotational speed of the galaxies. If you believe in Newton and Einstein, then you need additional matter to explain the observed rotational velocity seen in the universe. And then in addition, there is something called dark energy. I think that Ken maybe will later explain the dark energy. That comprises even larger. This comprises even larger part of the unknown. So maybe 3/4 of the energy of the universe is the dark energy, and we don't know what it is. And then we have more matter. We have only matter. We have no antimatter planets or antimatter. Why do we have matter and not antimatter? And why do the masses of these fundamental particles differ by 13 orders of magnitude? Then the people, anyway, gravity is not really included in the standard model, and it's very difficult to combine it with quantum physics and with the other forces. And then there is a search for a world equation, which has so far not been accomplished, although I think that some people tried to develop it 100 years ago already. Okay, so we are working on a future circular collider. In response to the upgrade of the so-called European Strategy for Particle Physics in 2013, they requested a study of a post-LHC collider complex after the Large Hadron Collider based at CERN. And this would be a larger circular ring. Here you see the LHC looks small as on Phil's shot, but here we don't talk about a long line, but we have another circle which is now 100 kilometers in circumference, which would go around the city of Geneva and the nearby mountain, which is called the Salève, and it would pass under the lake of Geneva. So we are quite fortunate. On this side, on the Geneva side, this lake is rather shallow, only 15 meters deep, while on the other side it becomes very, very deep on the opposite side at Montreux. So there's no problem. The LHC is about 100 meters under the surface, and this FCC will be probably 200 meters under the surface, so there is no issue going under the lake. But we are limited. We cannot build something much bigger than 100 kilometers because on the one side there are the Alps here, and on the other side there is the Jura mountain, and we don't want 1,000-meter deep access shafts, etc. So we are somewhat limited to this 100 kilometers. Now we would like to go up in energy in order of magnitude beyond the LHC. There are reasons to believe that going up in a factor 10 or so in energy will help us understand the Higgs mechanism, more properties of the Higgs particle, the potential of the Higgs, and also perhaps help us understand dark matter, and with luck, dark energy. So to go to 100 TeV in this large ring, we need 16 Tesla magnets, dipole magnets. The LHC has 8 Tesla, and that was already extremely difficult. And if we want to go from 8 Tesla to 16 Tesla, we need a new technology. So we need a new type of superconductor to make these magnets. There is a simple equation. So actually, energy of a Hadron Collider is very easy. It's just proportional to the magnetic field and the circumference. So we are increasing both. We are increasing circumference by a factor 4 almost, and we are increasing the magnetic field by a factor 2, which is already quite challenging. And together we get almost a factor 8 in energy. So if we build this new tunnel, we can also think about putting other colliders in this tunnel. For example, we can put an electron-positron circular collider, and that would have a very excellent performance at energies where we can produce a Higgs particle. So this would also be a very beautiful Higgs factory and also a nice factory of top quarks. So we can actually produce all the known particles and in very large quantities and measure with extreme precision to see any deviation from the standard model, which would give us a hint at which next energy scale in new physics should appear. Of course, we can also collide electrons with protons, as we did in Hera in Hamburg, where I started. So people who want to make a super Hera with 10 times higher energy and 10 to 100 times the luminosity. So this could also be possible. And in addition, we have a less ambitious study. We developed these 16 Tesla magnets. We could install these magnets also in the existing LHC tunnel, and that would allow us to double the energy of the Large Hadron Collider. This is a time scale of the large circular colliders at CERN. There was LAB, there was an electron-positron collider. The design started in the mid-1970s, and you see it took, I don't know, more than 10 years to design and construct it, and then it operated 12 years for physics, and there's the LHC. And this will be followed by high luminosity upgrades, which is an extension of the LHC to give 10 times the performance, which is called the high luminosity LHC. And so the LHC and high luminosity LHC will together run for about 25, 27 years, from 2010 to about 2037. So we have about 20 years time now to develop a concept for a future collider. So we have started this future circular collider design, which is actually 4 different colliders in one study. And we aim for a prototyping phase. If it is supported by the next update of the European strategy in 2019, we could go into a prototyping phase, a construction, and ideally, we would like to start the physics at this new machine when the LHC physics terminates, so in the second half of the 2030s. So we must advance fast now because we have less time available than had been available for the LHC, and this machine is much bigger and needs even more advanced technology, so we don't have so much time. And our intermediate goal is to have a solid conceptual design by the end of 2018. So we are about halfway in this process, and we are looking at all the items, including this construction schedule, the cost, the key technologies, and parameter space for operation. And the one goal is that we absolutely must ensure that the promised performance can be achieved. This has been the case for LAB and LHC. Both machines reached the design performance in a rather short time. And so in principle, we know that for this type of machine, we should be able to reach the promised performance. But the design study will ensure that there is enough margin to accomplish this. Okay, here is just a picture on the magnet technologies. For a long time, the United States was leading the high field magnet development in Berkeley. Already in the early 2000s, they reached a 16 Tesla field with this magnet here. And last year at CERN, we built a similar magnet, which also reached a 16 Tesla field. So in principle, we have a demonstration that with using the Niobium-3 tin superconductor, we can achieve 16 Tesla field, which is twice the field of the LHC magnets, which are based on niobium titanium superconductor. So, but we need some margin, so we are not quite there yet. These test magnets, they have no aperture for the beam, so we need to have a beam pipe inside the magnet to bend our particles and to bring them through this magnet. So we still need some development to have accelerator quality magnets at the 16 Tesla field. And also we like to make these magnets as cheap as possible, so there is a R&D effort to reduce the cost of the superconductor and of the magnets.
You got about minus a minute.
Minus a minute. My last slide. It shows you the Hadron Colliders unraveling the secrets of the universe. So there used to be the Tevatron in the Chicago at the so-called Fermi Lab. It was operated from 1983 to 2011 at 2 TeV center of mass energy. Then now we have the LHC, factor 7 higher energy, with both with important discoveries. And then we are planning to make the next step. And also, I would love the future to be linear. If we wanted to use this linear collider technology to build a 100 TeV collider, we would need 3,000 kilometers. And with this technology, we are staying below 100 kilometers. So there is still a way to go. We think that circular colliders are still the way forward if we want to see 100 TeV in this century.
Okay.
So, thank you.
Thank you, Frank. Thank you. All right. So we can start to see a little bit of a competition maybe developing between linear colliders and circular colliders. So a few key points there that we'll come back to in a bit was, first of all, the time scale of some of these projects, which I'll come back to. Second of all, that the electron-positron machines, in Phil's the linear collider version, sort of 3 kilometers long, maybe, 30 kilometers long, 50 kilometers long. But to actually do the same thing for hadrons would be, you say, 3,000 kilometers long. That's your estimate, approximately. Okay, so we're seeing there's some different physics involved there and how difficult it is to accelerate those particles and the energies you need to reach the physics that you're looking for, which we'll come back to in a bit. So the two other speakers here have slightly different viewpoints, I think. And one of the topics that Phil covered was synchrotron radiation, and that's a really important topic in building accelerators, because if you bend a particle around a corner, it loses energy. So at some point, you're just fighting to put that energy back in. And Ken, I think some of the machines you'll talk about have a different approach to tackling that. So
that's right.
Here you are.
Oh,
Hand over to Ken.
Yeah, so I think actually what's exciting is actually the breadth of science that can be addressed by these different techniques. So what I'm supposed to talk about is a different kind of particle that you could use to do the science. And so the jargon titles are neutrino factory and muon collider. The key thing is they accelerate muons, and I hope it will become obvious why. So here is the particle content of the standard model. You've seen that already. You've got quarks that make up what we call the hadrons. If you have up and down, you can make protons. You have electrons. That now means you can make atoms. And that's basically all you need for real life. There are two more families, and they're there, or sort of as you go to the left on that plot. And you've got a whole line of particles, which are called the neutrinos. So when I did the particle physics course at Imperial College in '98, they were massless. And then there was the discovery of neutrino oscillations, which means they are not massless. They have some mass. That means they do not go at the speed of light. They have no conserved quantum numbers. That's important. That means that a neutrino can change from being the partner of the electron to being the partner of the muon as it travels through space and time. So it's really like a traveling Schrodinger's cat. At 1 minute it's alive, at the next minute it's dead. And the good thing is that the weak interaction has got the opening the box thing, because of the weak interaction, picks out the flavor, and you can tell. So that's how we know that they've got mass. Okay, so I'm going to talk a little bit about the neutrinos. What we do technically is we take the neutrinos, we invent 3 mass eigenstates for them, so there are 3 types of neutrino that are distinguished by their mass. We mix them up, and that's how we get the flavors, and we want to measure the way in which that happens. Can you see that on the bigger screen? I can't see this. So here's the cosmic abundance of different particle types. And you'll notice that neutrinos are second only to the number of protons. No, it's on the right-hand side of the screen, I hope, in that figure. The other thing that you want to know is that the mass of neutrinos is way different from everybody else, several orders of magnitude different. So we found the Higgs fantastic. All the charged particles, we think, get their mass from the Higgs. Neutrinos are several orders of magnitude lower. Same mechanism, different mechanism, we need to find out. Okay. Here's the history of the universe, starting from the Big Bang.
In one slide.
in one slide, yeah. So the important thing is that neutrinos really have some impact here. So the impact of neutrinos. So if we start at the recent past, we know that the universe is expanding, and we know there is dark matter in the universe, as was already explained. We know there's dark energy. So neutrinos are rather special. They don't have conserved quantum numbers. They've got mass. We don't know how they got the mass. And those theories, in principle, offer explanations for those. We need to understand the neutrinos. Neutrinos are almost massless. They're not massless. So they go almost at the speed of light. They only interact weakly, so they can communicate over vast distances of space and time. So they can contribute to making the universe look uniform on large scales. So large-scale structure and also galaxy formation might be to do with neutrino mass. Inflation. So inflation is really important, and the Bank of England tries to deal with it. But particle theorists look at phase transitions of particles in the early universe, and there are theories which have really, really heavy neutrinos, which are partners to the ones that we observe, and the phase transition where they go out of interaction is perhaps driving the inflation, so we need to understand neutrinos. And finally, if you meet antimatter, you will annihilate. There is no antimatter. We can calculate from the bodies in this room a very strong limit on the amount of antimatter in the universe, and nobody can explain that. There are theories, so they're the same as the ones that are generating this inflation, that take all the antimatter away. We really need to understand neutrinos. Okay, so here's the evolution of the universe on a different scale, and what you're seeing is where the different accelerators contribute. The LHC, if you can pick it out, I can point at this screen, but it's useless. So you can see where the LHC contributes. Accelerators today go up to the yellow line, the white line, which is on the left-hand side, the vertical white line. So you want to go beyond, and there have been 2 or 3 ways of getting there that have already been described. That's really exciting. There's another way, which I want to explain here. Right, so there is an electron. That's what you need to make matter. There's another particle which has exactly the same properties. It's called the muon. The only way it differs from the electron is that it's 200 times as heavy, and it decays into an electron and actually into neutrinos. The fact that it's 200 times as heavy makes it technically good to do the kind of things that you can do with electrons and positrons. So you can accelerate them, they're heavy, you can do that efficiently, and actually you can show that it's more cost-effective if you can produce enough of them. They decay, in particular they decay democratically into muon and electron neutrinos, and that's critical for what you need to do the science. You need new E's because you need to look at transitions that are not disappearance. So you need to see a neutrino turn into something else.
So just to be clear, nu is the symbol you give for the neutrino, right?
Yeah. Thank you,
right.
Suzie. Okay, so for both the energy frontier, so how do you get the very, very high energy, and how do you study the properties of neutrinos, muons are ideal because they're heavy and they decay to the right particles. There is a problem, and that is that they decay. So the advantage is also the disadvantage. They decay in 2.2 microseconds if they are not moving. And you produce them from the decay of pions. So once you've got your muons, they typically occupy a large volume. So I want you to think of a watermelon in 3-dimensional space, but they're highly divergent. The cost of your acceleration is roughly going as the size squared, and then you've got the stored energy. So there's a real premium in making it smaller. To study neutrinos, you've got to turn the watermelon into a cucumber because the length is okay, but the width you've got to shrink down. And so that means that what we have to do is demonstrate a technique to reduce the phase space. That's ionization cooling. What we do is we shoot the muon beam through an absorber. It loses energy. That means the momentum transverse to the beam and the longitudinal momentum go down equally. You accelerate in one direction. That means the ratio has gone down, and you've squeezed the beam down. Experiment we're doing at Rutherford Lab now is going to demonstrate that. So you look at the top, which is the concept. You can see how we want to realize it, and that's what it looks like in the hall. So I'm only saying that we're going to demonstrate the key technology, and then we can make the accelerators that can do what I just tried to explain. And to finish on the size of this thing, on the left-hand side with the red squiggle, you can see the border of the Fermi National Accelerator Laboratory in the US. And you can see the Muon collider fitting on that site. For comparison, you can see the LHC, that's the blue circle, the ILC, which is the green line, or click. And on the right-hand side is what used to be called the VLHC, so it's roughly speaking the FCC that Frank was just describing. So it's not that, so these are different techniques, they do slightly different science, and I think there's a great strength in the breadth of science that you can do with these different things. Thank you very much.
Okay, thank you. Good. So one of the key things I should point out at this stage is that one of the useful things about muons is because they're slightly heavier, they emit less synchrotron radiation. So this issue of the beam losing energy as it goes around a ring is not such an issue in the muon collider, right?
I think that the point to make is that if you're radiating energy, but you want to keep colliding at the same energy, you've got to put the energy back. And that has to come out of the power station. So if you radiate less energy, you have to put less power in, and that's why there is an energy, about 1.5 TeV, where the muon colliders are more cost-effective to operate, maybe not to build.
Okay. Right, so now onto something completely different. I don't think I need to introduce any further than that, just completely different. Go ahead, Stuart.
Oh, hang on. Oh, started on the wrong one. So far, you've heard about all these different particle accelerators and future projects, and I think they have one thing in common. They're all massive machines. And so if you like, what the question I'm looking at is why are they so big, and more importantly, can we make them a lot smaller? Phil was right. I'm not sure about I agree with the 50 years, but we are talking about a technology that could be used a bit further in the future. I'm very happy with that. But, yeah. I again, compulsory picture, overhead picture of a big accelerator. Here is, I went for SI units rather than miles. So it's about 3 kilometers long. This is SLAC in America. And the thing is that all of these particle accelerators are basically using the same technology to accelerate particles. Okay? Whether or not they're accelerating electrons, protons, or muons, they're using an electric field to accelerate a particle inside a vacuum tube. So it's a low-pressure vessel with nothing inside it, and then you put a radio frequency wave traveling through it, which accelerates the particles up as it goes along. You can work out the energy that your charged particle can get up to by just taking the strength of the electric field, which is measured in volts per meter, or megavolts per meter, if you like, million volts per meter, by the distance. Okay, so because they're all using basically the same technology, they're all working at around about 10 to 100 right at the top end, 100 megavolts per meter. So just some very simple math. That tells you if you want to get a particle to just 1 GeV, you still need 10 to 100 meters of accelerator. If you want to get to 100 GeV, then you need, depending on the technology, between 10 and 100 kilometers. I didn't put 100 TeV on there, but that would be those numbers. And so effectively the only way we can make things shorter is, well, there are two ways. One is we can use the same accelerating structure over and over again, which is a circular accelerator, but then we hit the problem of magnet strength and synchrotron radiation, or we can turn up the electric field strength. They're basically the only two things we can do. In fact, the technology to get up to 100 megavolts per meter, that's already really hard. Yeah, that's a really cutting-edge technology in vacuum accelerators. And why can't they go any higher? Well, the problem is, I don't know if you've ever tried this, but if you have 2 electrodes and you put a large voltage between them in air, you get a spark forming between them. Yeah, if you turn down the pressure, so if you put that capacitor in vacuum, you can put a larger voltage before you get breakdown. But it doesn't matter how low in pressure you go, you will always get to the point where there's just one electron or 1 or 2 electrons between those 2 plates, and that will cause an avalanche that will mean that you get sparks forming inside your accelerator. And that's the sort of fundamental limit of why, if you're using this conventional technology to accelerate things, you can't go any higher than about 100 megavolts per meter. And that's because you turn up the field, and it's just going to start forming sparks, which degrade the whole structure. They may even destroy it. And so, if you like, what I'm trying to look at, and I have been for the last decade or so, is could we do something else? Could we actually solve this breakdown problem and start with something that one thing, it would be nice if you could find something that just didn't break down. I'm not sure that exists. But instead, actually do the acceleration in something that's already broken down. So if you take a volume of gas and you fully ionize it, it can't ionize anymore. And actually, that's called a plasma, and plasmas can support huge electric fields. I think we have already demonstrated sort of fairly useful fields, depending on your definition, at 10,000 megavolts per meter. So just to give you an idea of, I would say compared to conventional accelerators, it's very early days. We've been doing things for a while, in my lifetime, in terms of how long I've been doing it, and significantly before me as well. But there are, did my microphone just go off? Yeah, it's come back on. Okay, but there are definitely things going on. So this picture here is an overview of the Rutherford Appleton Lab, one of the national labs in the UK here, and there are 3 GeV, so small, particle accelerators in this picture. The first one is at the top here. That's the diamond light source. It's a machine not for doing particle physics, but for making X-rays for all sorts of scientists. And at the heart of it is a 3 GeV electron beam. In the bottom here is ISIS, which is a neutron source, and those neutrons are made by accelerating protons and using a process called spallation to make neutrons. And at the heart of that is a sort of 1 GeV proton accelerator, 0.8, I think. And then, so they're all, pretty big machines. Somewhere in that building, in there, there is a pretty big laser called Astra Gemini, which we're now fairly routinely producing, very messy compared to the beams that come out of these machines, but 2 GeV beams inside that lab there. The actual accelerator is this long. Okay, so the actual plasma part is that long. And so the technology we're working on is, I really like what Phil said, is that if you could imagine replacing conventional accelerators with a plasma system, you could suddenly make a massive upgrade. So that's the sort of thing, the timescale I think seems realistic. But just to give you an idea of how much progress we're making, here I've got a plot from one of my PhD students' thesis, Jason Cole. So he took conventional electron accelerators and their sort of energy as a function of time. So you can see they started back in the 1940s, and they've made rapid progress for the first 30 years, doubling energy about every 2 years, I think it was, and then it kind of tailed off. And then you get plasma accelerators, which basically started in the mid-90s, and we've been making similar progress over the last 10 years, 10, 20 years as well. So our record is now, the group at Berkeley have now produced 4 GeV electron beams in just a plasma that's 9 centimeters long, so that big. And that corresponds to an accelerating field that is 10,000 megavolts per meter. So I haven't done the numbers, but if you wanted to do this 100 TeV machine, if you could use that, it would get a lot shorter. So that's what I'm working on. Thank you very much.
Okay, thanks.